So let us start with our chapter Thermodynamics second introduction. A need for the second law and different statements of the law. First law of thermodynamics had certain serious limitations. To overcome these limitations, a strong need was therefore felt to introduce another law called the second law of thermodynamics. A few limitations of the first law and as a consequence some definitions given to the second law are briefly given below. First, the major limitation of first law of thermodynamics is that it merely indicates that in any process there is an exact equivalence between the various forms of energies involved, but it provides no information concerning the feasibility of the process, that is whether the process is possible or not. For example, the first law doesn't indicate whether heat can flow from a cold end to a hot end or not. All that it tells is that if this process occurred, heat energy gained by one would be exactly equal to that lost by the other end. Similarly, the first law doesn't tell whether a gas can diffuse from low pressure to high pressure or water can itself run uphill, etc. Second law supplies answers to the above questions by stating that all spontaneous processes like the flow of heat from hot end to cold end, diffusion of gases from high pressure to low pressure, or the flow of water down a hill, etc., are thermodynamically irreversible. First definition. The term spontaneous process used in the above definition means a process which can take place without the help of any external agency. All natural processes, some of which are mentioned in the definition above, are spontaneous processes. However, it may be mentioned here that the term spontaneous doesn't give any idea of the rate of the process, that is, whether the process takes place fast or slowly. All that it implies that is that if that process can occur without the help of an external agency. First law states that when heat is converted into work, the work obtained is equivalent to the heat absorbed. However, it has been seen from experience that the heat absorbed cannot be completely converted into work without leaving some change in the system or the surroundings. For example, the heat produced in a locomotive is not fully utilized in running the train. A part of it is lost to the surroundings or wasted in overcoming the friction. Hence, the second law is also stated as follows. Complete conversion of heat into work is impossible without leaving some effects elsewhere. This is the second definition. Besides the above definitions, a number of other definitions have also been given to the second law of thermodynamics. The two important ones are: it is impossible to construct a machine functioning in cycles which can convert heat completely into the equivalent amount of work without producing some changes elsewhere. Third definition: without the use of an external agency, heat cannot by itself pass from a colder body to a hotter body. The term functioning in cycles is introduced in the above definition to indicate that the machine must return to its original state at regular intervals so that it can function continuously. Further, it may be recalled that in an isothermal reversible expansion of an ideal gas, delta U is equal to 0, so that Q is equal to W. That is, the work done is exactly equal to the heat absorbed by the system. In other words, if this process heat is completely converted into work, however, it is important to observe that this conversion is accompanied by an increase in volume of the gas so that the system has undergone a change. A number of other definitions have also been given to the second law of thermodynamics, which will be come across in the succeeding sections of this chapter. Fraction of heat absorbed by a machine that it can transform into work is called the efficiency of the machine. Thus, if Q is the heat absorbed and W is the work done, then the efficiency of the machine is given by eta is equal to W upon Q. The machine used for the conversion of heat into work is called heat engine. In order to bring about this conversion, the heat engine absorbs heat from a reservoir at a higher temperature called the source, converts a part of it into work and to the remainder returns the remainder to the heat reservoir at a lower temperature called the sink. In order to calculate the efficiency of any heat engine, Sadi Carnot devised a technique called Carnot cycle. A cycle is a process in which system returns to its original state after a number of successive changes. A process conducted in this manner is called a cyclic process. Engine chosen by Carnot, called Carnot engine, for the purpose of the calculation of efficiency was a hypothetical one. and cannot be achieved in actual practice. It was selected because it could be subjected to a simple thermodynamic treatment. It consists of a cylinder containing 1 mole of an ideal gas as the working substance and fitted with weightless, frictionless piston so that all the operations in the cycle are carried out reversibly. For this reason, it is also called a reversible heat engine. The cylinder is supposed to be insulated on all sides except at the bottom so that heat can flow to or from the system only through the bottom. Further, it is supposed that there are two heat reservoirs, one at a higher temperature T2 called the source and the other at a lower temperature T1 called the sink. If some operation is carried out by placing the cylinder in the source or the sink, it can exchange heat with it and hence the operation temperature remains constant so that the process is isothermal. On the other hand, if during an operation the cylinder is placed on an insulating material, no heat exchange can take place between the system and the surroundings and hence the process is adiabatic. Carnot cycle consists of four different operations which can be represented on a pressure volume diagram, sometimes called as an indicator diagram. These operations are carried out as shown and briefly described below. Alternatively, the cylinder may have conducting walls as well as the bottom, and the source and sink may be two thermostats. For carrying out isothermal processes, the cylinder may be placed in the thermostats. For carrying out adiabatic processes, the cylinder may be placed in a perfectly non-conducting jacket. The cylinder containing 1 mole of the ideal gas occupying a volume V1 is placed in contact with the source heat reservoir at a temperature 2. This is the process of isothermal expansion. The gas absorbs heat Q2 from the source and expands isothermally and reversibly till its volume has increased to V2. Path of the process is represented by the isothermal curve AB. Since the gas is ideal, the work W1 by 1 mole of the ideal gas will be given by minus W1 is equal to RT2 ln V2 by V1. Further, for an ideal gas, the work done is equal to the heat absorbed Q2 so that minus W1 is equal to Q2 is equal to RT2 ln V2 by V1. Here W1 has been taken as negative and Q2 as positive by the latest SI conventions of sign. Adiabatic expansion. Second process. The cylinder is now removed from the source and placed in perfectly insulating material so that the gas now expands adiabatically and reversibly. Work is done in the expansion, but since no heat enters or leaves the system, the temperature must fall. The reversible adiabatic expansion is continued till the temperature has fallen to T1, which is the temperature of the sink. Suppose the corresponding volume becomes V3. The path is shown by the adiabatic curve BC in figure 2.1. The work W2 will be given by minus W2 is equal to CV T1 minus T2, where CV is the heat capacity of the ideal gas. Here W2 is negative by the usual conventions of sign. Isothermal compression. Third, the cylinder is now removed from the insulating material and placed in contact with the sink, that is the heat reservoir at a lower temperature T1. Gas is compressed isothermally and reversibly till the volume decreases from V3 to V4. The process is represented by the path CD in figure 2.1. Work done is taken as positive by the usual conventions of sign and hence will be given by W3 is equal to RT1 ln V4 by V3. During the operation, an amount of heat Q1 exactly equal to W3 will be returned to the sink at T1. That is, heat has been given out by the system. Using the appropriate conventions of sign, Q1 will be negative and W3 will be positive. So that minus Q1 is equal to W3 is equal to RT1 ln V4 by V3. Adiabatic compression. The cylinder is now removed from the sink and placed again on the insulating material. The gas is then compressed adiabatically and reversibly along dA till the initial state A has been regained. Temperature of the gas rises from T1 to T2. The work done is positive by the conventions of sign and it will be given by W4 is equal to CV T2 minus T1. As a result of these four operations, the system has returned to its original state so that a reversible cycle has been completed. Net work done by the system will be given by W is equal to minus W1 plus minus W2 plus W3 plus W4. Here are the equations of these four works. RT2 ln V2 by V1 minus CVT2 minus T1 plus RT1 ln V4 by V3 plus CVT2 minus T1 is equal to RT2 ln V2 by V1 plus RT1 ln V4 by V3. Since V1 and V4 lie on one adiabatic curve and V3 and V2 lie on another, it follows that V4 by V1 gamma minus 1 is equal to T2 by T1. V3 by V2 gamma minus 1 is equal to T2 by T1. Comparing equations 9 and 10, we get V4 by V1. We get V4 by V1 gamma minus 1 is equal to V3 by V2 gamma minus 1, or V4 by V3 is equal to V1 by V2. Putting this value in equation 8, we get RT2 ln V2 by V1 plus RT1 ln V1 by V2 equal to RT2 minus T1 ln V2 by V1. Hence, dividing equation 12 by equation 2, we get W by Q2 is equal to T2 minus T1 upon T2, which gives the efficiency of the Carnot cycle or engine. Now, Carnot theorem. From equation 13, it is clear that the efficiency of a reversible heat engine depends only upon the temperatures of source and the sink and is independent of the nature of working substance. Another important observation to be made from the above derivation is that the work done in the cycle is only the one involved in the isothermal operations, because that work done in the adiabatic operations second and fourth cancel each other. Further, as discussed earlier, the work done in a reversible isothermal expansion from A to B is maximum, whereas the work done on gas during a reversible isothermal compression from C to D is minimum. Hence, the work done by the system, that is the reversible heat engine or Carnot cycle, is maximum for the specified conditions, and therefore the efficiency is maximum. The result that follows from the Carnot cycle as derived is called the Carnot theorem. It may be stated as the efficiency of a reversible heat engine depends only upon the temperatures of source and the sink and is independent of the nature of the working substance. In other words, all the reversible heat engines working between the same two temperatures have the same efficiency. Further, it states that the efficiency of a reversible heat engine is maximum for the given temperatures. Since the quantity T2 minus T1 is always less than unity, the efficiency of heat engine is thus always less than unity. In view of the above discussion, the second law of thermodynamics is sometimes defined as follows. A heat engine absorbs a certain amount of heat from the source, converts a part of it into work, and returns the rest to the sink. In other words, it is impossible to convert heat completely into work. Combining equations 258, we get W is equal to Q2 minus Q1. That is, net work done by the system is equal to net heat absorbed by the system. Putting the value of W in equation 13, Q2 minus Q1 upon Q2 is equal to T2 minus T1 upon T2. Efficiency of a heat engine may be given by any of the following expressions. Eta is equal to W by Q2 is equal to Q2 minus Q1 by Q2 is equal to T2 minus T1 by T2. This results derived for a reversible Carnot cycle leads to the introduction of a new thermodynamic term called entropy, as discussed in next section. So from our earlier studies, we are familiar that a thermometer is constructed most commonly by taking suitable amount of mercury in a glass bulb at the end of a capillary tube and marking 0 when it is placed in contact with ice, and marking 100 when it is placed in the boiling water. The length between the 2 points is then divided into 100 equal parts called degrees. The scale of the temperature thus obtained is called Celsius scale of temperature. However, because different liquids expand to different extents, that is, their coefficients of expansion are different, and also they do not uniformly expand over a given range, thermometers constructed by using different liquids will show different numerical values of temperature between their fixed points. For example, a body may show a temperature of 28.7 degrees Celsius with mercury thermometer, but may show 28.8 degrees Celsius with an alcohol thermometer. The problem was solved by study of the properties of gases. It was found that an ideal gas of a perfect gas ceases to exist at a temperature of minus 273.15 degrees Celsius. This temperature was called 0 degree absolute. The scale developed on this basis is called perfect gas temperature scale and is found to be independent of the ideal gas taken. However, based on the efficiency of a reversible heat engine, Lord Kelvin was the first to develop a scale of temperature that was independent of the nature of the gas taken in the heat engine. This scale of temperature is called thermodynamic scale of temperature or Kelvin scale of temperature. It is found to be identical with the ideal gas temperature scale. The basis of the development of the scale is briefly described. Suppose there are two constant temperature heat reservoirs, one acting as a source and the other as a sink, and a reversible heat engine operates between them. Temperature of each reservoir on the new scale may be taken as proportional to the quantity of heat absorbed from the source and the heat lost to the sink, both of which can be measured. If Q2 is the heat transfer from the source, that is heat reservoir at higher temperature, and Q1 is the heat transfer in the sink, that is heat reservoir at a lower temperature, then if their temperatures on the thermodynamic or Kelvin scale are represented by theta 2 and theta 1 respectively, we shall have Q2 by Q1 is equal to theta 2 by theta 1. This ratio of two temperatures has been defined in the manner independent of the nature of thermometric substance. Taking the reciprocals of both sides of equation, subtracting the result from unity, we get Q2 minus Q1 upon Q2 is equal to theta 2 minus theta 1 upon theta 2. Putting theta 1 is equal to 0, that is 0 of new scale. Q2 minus Q1 upon Q2 is equals to 1. This implies that the 0 on the Kelvin scale is the temperature of the sink for a reversible heat engine whose efficiency is unity, that is, which is capable of converting heat completely into work. But from equation 14 on page 86, it may be seen that it is possible only at absolute 0 on the ideal gas scale of temperature. This leads to the conclusion that the Kelvin scale and the gas scale are identical provided the gas is ideal. The temperatures on the thermodynamic scale are therefore expressed in terms of degree Kelvin. Further, it has been found that if the lower fixed temperature is taken as equal to that of triple point of water, that is 273.16, then Kelvin is exactly equal to Celsius degree. For this reason, the temperatures on the absolute scale in which melting point of ice is taken as 273.16, it is often referred to as degree Kelvin. It may be concluded the thermodynamic scale of temperature is defined as the basis on the second law of thermodynamics is more basic than that based on ideal gas because any fluid can be used. However, the ideal gas scale is more practical for laboratory use. Concept of entropy. Entropy is a state function. For a reversible Carnot cycle working between temperatures T2 and T1, it has been seen that Q2 minus Q1 upon Q2 is equal to T2 minus T1 upon T2, where Q2 is the heat absorbed isothermally and reversibly at temperature T2, and Q1 is the heat lost isothermally and reversibly at temperature T1. The above equation may be simplified as 1 minus Q1 by Q2 is equal to 1 minus T1 by T2, or Q2 by T2 is equal to Q1 by T1, or Q by T is equal to constant. Thus we conclude that the heat absorbed or lost isothermally and reversibly divided by the absolute temperature at which the heat is absorbed or lost is a constant quantity for a particular system. Further, in equation 2, Q2 is the heat absorbed at temperature T2 and Q1 is the heat lost at temperature T1. If Q1 were the heat absorbed at temperature T1, equation 2 would be written as Q2 by T2 is equal to minus Q1 by T1, integrating Q by T is equal to 0. Now consider any reversible cycle ABA. It may be regarded as being made of a number of Carnot cycles drawn across the diagram as shown, starting from A and going through all the cycles successively from A to B. It can be shown that all paths inside the closed curve ABA cancel each other, leaving only the zigzag path which is almost the same as the path ABA of reversible cycle. By making each Carnot cycle smaller and increasing their number, it can be made to correspond more closely to ABA. The reversible cycle can therefore be regarded as being made of an infinite number of Carnot cycles. For each of these cycles we have integrating Q by T equals to 0 as proved above. Hence, for an infinite number of cycles, integration of del Q by T is equals to 0, where del Q is a very small quantity of heat absorbed at temperature T during the small isothermal change of the reversible process. Therefore, integration q by t is equal to integration a c b q by t plus integration of b say a q by t del q by t is equal to 0. Or may write q by t given a say b is equal to minus q by t b say a. This implies that the total volume of the quantity this implies that the total volume of the quantity q by t is for the path a to b is equal to the total value of this quantity same q by t for the reverse path b to a. Hence, it may be concluded that the quantity q by t is a state function. Its value depends only upon the initial state A and final state B and is independent of the path. Obviously, q by t is the change in the value of a quantity or a function having some definite values at A and B depending upon the values of pressure, volume, and temperature. This quantity or the function is called entropy and is usually represented by symbol S. Thus, if SA is the value of entropy at A and SB is the value at B, then we must have q by t is equal to SB minus SA is equal to delta S, where delta S represents the total change in entropy in going from initial state A to final state B. Hence, entropy may be defined as a state function, that is the change in the value which from the initial state to the final state is equal to the quantity q by t, that is the total heat absorbed reversibly and isothermally in going from the initial state to the final state divided by the absolute temperature at which the heat is absorbed. From equation 6, the from equation 6 the entropy change may be defined directly as the quantity of heat absorbed isothermally and reversibly divided by the absolute temperature T at which this is absorbed. It is important to note that as entropy is a state function, therefore the value of entropy change during a process should not depend upon the path, that is whether the heat is absorbed reversibly or irreversibly during the process. However, since the derivation of above result is based upon Carnot cycle in which the heat is absorbed reversibly, therefore the expression 6 for the entropy change is valid only when the heat is absorbed reversibly. Thus, it is better to use the symbol q reversible in place of q. The expression 6 may therefore be written as delta S is equal to q reversible by t. Further, as entropy is a state function, a small change in its value can be represented by ds. Hence, we may write ds is equal to q reversible by t. From the expression delta S is equal to q by t, it is observed that the units of entropy will be calories per degree if heat is expressed in calories. Further, entropy is an extensive property. It is therefore important to mention the quantity of substance involved. It is usually expressed for 1 mole of the substance. Hence, the entropy units are calories per degree per mole. If heat is measured in joules, the units of entropy will be joules per degree per mole. Suppose a process occur under completely reversible conditions. That is, the heat is absorbed by the system reversibly and the heat is lost by the surroundings also reversibly. If Q reversible is the heat absorbed by the system reversibly, then the heat lost by the surroundings will also be Q reversible. If the process takes place isothermally at the absolute temperature T, then entropy change of the system will be given by delta S system is equal to Q reversible by T. Entropy change of the surroundings will be Q reversible minus Q reversible by T. Hence, the total entropy change for the combined system and surroundings will be delta S system plus delta S surroundings is equal to Q reversible by T minus Q reversible by T is equal to 0. Thus, we may conclude that in a reversible process, the net entropy change for the combined system and surroundings is 0. That is, there is no net change in the entropy. Second, entropy change in an irreversible process. If any part of the process is irreversible, the process as a whole is irreversible. Suppose that the total heat lost by the surroundings is Q irreversible. This heat will be absorbed by the system, but the entropy change of the system doesn't depend upon the heat actually absorbed, but it depends upon the heat absorbed irreversibly. That is on the quantity Q reversible. So if the heat is absorbed isothermally by the system at absolute temperature T, the entropy change of the system will be given by delta S Q reversible by T. Further, suppose that the loss of heat Q irreversible by the surroundings takes place infinitesimally slowly, that is, reversibly and isothermally at the temperature T, then the entropy change of the surroundings will be given by delta S surroundings minus Q reversible by T. The total entropy change for the combined system and surroundings will therefore be delta S system plus delta S surroundings is equal to Q reversible by T minus Q irreversible by T. We know that the work done in a reversible process is the maximum work, that is W reversible greater than W irreversible. Further is the internal energy. Further is the internal energy. U is a state function. Its value of delta U is the same whether the process is carried out reversibly or irreversibly. Hence delta W is equal to Q reversible minus W reversible is equal to Q irreversible minus W reversible. Combining results 4 and 5, we conclude that Q reversible is greater than Q irreversible. Therefore, Q reversible by T greater than Q irreversible by T, or Q reversible by T minus Q irreversible by T greater than 0. Thus, it may be concluded that in an irreversible process, the entropy change for the combined system and the surroundings is greater than 0. That is, an irreversible process is accompanied by a net increase of entropy. Since all the spontaneous processes are thermodynamically irreversible, first definition of second law of thermodynamics, it may be stated that all spontaneous processes are accompanied by a net increase of entropy. This is also one of the very common statements of second law of thermodynamics. The results for the entropy change in a reversible process and that in an irreversible process may be combined together and put in the form delta system plus delta surroundings greater than equals to 0, where the sign equals to stand for the reversible process and the sign greater than stands for the irreversible process. The exact calculation of total entropy change during an irreversible process, that is when heat flows from a body B at a higher temperature T2 to a body B to a body A at a lower temperature T1, when brought in contact with it, may be carried out as follows. Suppose the heat lost by the body B is represented as Q irreversible. The flow of heat may be allowed to take place infinitesimally slowly so that it is absorbed by the body A reversibly and isothermally at T1, which may be represented as Q reversible. Entropy change of body B will also depend only on Q reversible, hence entropy change of body B is minus Q reversible by T2. Entropy change of body A is plus Q reversible by T1. Minus sign indicates decrease in entropy while positive sign indicates increase. Delta S total is equal to minus Q reversible by T2 plus Q reversible by T1 is equal to Q reversible 1 upon T1 minus 1 upon T2. Combined system in the surroundings is sometimes called as an isolated system. The results derived in section this 2.6 and 7 are thus for the isolated system. Negative sign with W has been used as it is a work of expansion. Coming on to our next topic, that is Clausius inequality. As discussed above, for an isothermal for an irreversible process, the result given in equation 9 may be written as delta S system plus delta S surrounding greater than 0, or delta S system greater than minus delta S surroundings. Also from equation 2, page 91, we have delta S surroundings is equal to minus Q by T. Putting this value in equation 2, we get delta system greater than Q by T. For small changes, the above equations may be written as ds system greater than minus ds surroundings, ds system greater than dq by t. Expressions 4 and 6 are the expressions of Clausius inequality. These equations shows that irreversible processes are accompanied by an increase of entropy. This is further illustrated with the help of the following two examples of irreversible processes. Spontaneous expansion, irreversible adiabatic expansion. Suppose the system undergoes irreversible adiabatic change, then as dq is equal to 0, hence by Clausius inequality ds system greater than 0, that is the entropy of the system has increased. Further, as dq is equal to 0, this means that no heat is transferred into the surroundings, thus ds surroundings is equal to 0, hence total entropy change ds total is equal to ds system plus ds surroundings is equal to ds system. But ds system greater than 0, hence ds total greater than 0. Second is irreversible isothermal expansion. We know that when a perfect gas expands isothermally, its internal energy remains constant, that is du is equal to 0. Hence, according to first law of thermodynamics, du is equal to dq plus dw, and dq is equal to minus dw. If the gas expands freely into vacuum, no work is done, so that dw is equal to 0. Substituting in equation 7, we get dq is equal to 0. Hence, by Clausius inequality, ds system greater than 0. Further, as dq is equal to 0, this implies that ds surroundings is equal to 0. Hence, the total entropy change as in the above case is ds total greater than 0. Second is spontaneous cooling. Suppose heat is transferred from one system at a higher temperature T2 called the source to another system at a lower temperature T1 called the sink. If heat dq leaves the source and enters the sink, entropy change of the source is minus dq by T2. Entropy change of sink is plus dq by T1. Total entropy change is ds total dq by T1 minus dq by T2 is equal to dq 1 upon T1 minus 1 upon T2. As T2 very greater than T1, ds total is equal to positive, that is cooling transfer of heat from hot body to cold body is accompanied by increase of entropy. Entropy change of the universe, since all spontaneous processes occurring in nature are thermodynamically irreversible, these are accompanied by increase of entropy. Hence, it may be concluded that the entropy of the universe is continuously increasing. This result is sometimes taken as another statement of second law of thermodynamics. Thus, the main ideas of first and second law of thermodynamics may be summed up in the following statement. Energy of universe is constant, whereas the entropy of universe is continuously increasing and tends to a maximum. Consider 1 mole of an ideal gas enclosed in a cylinder fitted with a frictionless piston. If an infinitesimally small amount of heat del Q is supplied to the system reversibly and isothermally at the temperature T, then the entropy change accompanying the process will be given by ds is equal to del Q reversible by T. According to Flot, that is first law of thermodynamics, for an infinitesimal process, del Q is equal to du minus del W. If the process is carried out reversibly, equation 2 may be written as del Q reversible is equal to du minus del W. Further, if the work is restricted to the work of expansion, as is usually the case of the process considered in chemical thermodynamics, then minus del W is equal to PdV, where dV is the small increase in volume and P is the pressure of system, which is very nearly equal to the external pressure because the process is carried out reversibly. Putting the value of del Q from equation 4 in equation 3, we get del Q reversible is equal to du plus PdV. Substituting this value in equation 1, we get ds is equal to du plus PdV by T, or it may be written as TdS is equal to du plus PdV. For 1 mole of an ideal gas, we know that Cv is equal to du by dt, du is equal to Cv dt, where Cv is the molar heat capacity at constant volume and Pv is equal to RT, P is equal to RT by V. This is ideal gas equation, where V is the volume of system at higher temperature T and pressure P and R are the gas constant. Putting the value of du and P from equation 7 and 8 in equation 6, we get TdS is equal to Cv dt plus RT by V dV. ds is equal to Cv dt by T plus R dV by V. If the volume changes from V1 to V2, when the temperature changes from T1 to T2, then the entropy change accompanying the complete process will be given by ds S1 से S2 is equal to T1 से T2 Cv dt by T plus V1 से V2 R dV by V. Assuming that Cv remains constant in the temperature range T1 to T2, equation 10 may be written as ds S1 से S2 is equal to Cv T2 से T1 से T2 dt by T plus R V1 by V1 से V2 dV by V. Hence, delta S is equal to Cv ln T2 by T1 plus R ln V2 by V1. This is an expression for the calculation of entropy change for 1 mole of the ideal gas accompanying the process when temperature changes from T1 to T2 and volume changes from V1 to V2. Further, for 1 mole of an ideal gas, P1 V1 is equal to RT1 for the initial state, P2 V2 is equal to RT2 for the initial state. Dividing 13 by equation 12, we get P2 V2 is equal to P2 V2 upon P1 V1 is equal to T2 by T1. V2 by V1 is equal to T2 P1 upon T1 P2. Delta S is equal to Cv ln T2 by T1 plus R ln T2 P1 upon T1 P2. Further, we know that Cp minus Cv is equal to R, Cv is equal to Cp minus R, delta S is equal to Cp minus R ln T2 by T1 plus R ln T2 P1 upon T1 P2. Cp ln T2 by T1 minus R ln T2 by T1 plus R ln T2 by T1 plus R ln P1 by P2. सो डेल्टा एस की वैल्यू क्या हो जाएगी, सी पी एल एन टी टू बाई टी वन प्लस आर एल एन पी वन बाई पी टू. This is an expression for the calculation of the entropy change of one mole of an ideal gas accompanying a process when temperature changes from T1 to T2 and the pressure changes from P1 to P2. Entropy change of an ideal gas in different processes. Equation 11 gives the entropy change for one mole of ideal gas when the temperature and volume are variables. Similarly, equation 16 gives the entropy change of one mole of ideal gas when temperature and pressure are variables. These equations are modified if conditions of constant temperature, pressure, or volume are imposed. If temperature is kept constant for an isothermal process, T1 is equal to T2. Hence 11 and 16 equations are reduced to delta S is equal to R ln V2 by V1 is equal to R ln P1 by P2. Alternatively, these expressions can be derived directly. Delta S is equal to Q reversible by T minus W max is equal to Q reversible is equal to nRT ln V2 by V1, nRT ln P1 by P2. Substituting the values Q reversible from equation 19 and 20 in equation 18 and putting n is equal to 1 for 1 mole of ideal gas, we get the result equation in 17. If pressure is kept constant, that is for isobaric process, for an isobaric process, P1 is equal to P2. Equation 16 is modified to delta S is equal to Cp ln T2 by T1. If volume is kept constant, that is for an isochoric process, V1 is equal to V2. Equation 11 is therefore reduced to delta S is equal to Cv ln T2 by T1. Note carefully that all the expressions derived above for the calculation of entropy change involve natural logarithms. Since logarithmic tables commonly used are at a base to 10, in applying these formulae, ln x has to be first replaced by 2.303 log x, where x is quantity like T2 by T1, V2 by V1. Further note that if a gas expands reversibly but adiabatically, then as for such a process, Q reversible is equal to 0, then delta S is equal to 0. Entropy change during physical change, that is phase change. A change of phase occurs in any of the following cases: when solid melts, or conversely when a liquid freezes, when a liquid evaporates, or conversely when a gas condenses, when one crystalline form changes into another. When the change of phase commences, the temperature remains constant till the change of phase is completed. The heat evolved or absorbed during the phase change thus does not change the temperature and is therefore called latent heat. It is further termed as latent heat of melting, latent heat of vaporization, depending upon the nature of processes involved. In general, delta LH is the latent heat and T is the temperature at which the change of phase occurs. Entropy change accompanying the phase change will be given by delta S is equal to latent heat upon temperature T. Entropy change delta S is termed as entropy of melting, entropy of vaporization, depending upon the nature of processes. For example, we have entropy of melting or fusion, delta S F is equal to delta fusion H upon Tf. Delta fusion is the latent heat of fusion and is the melting. Tf is the melting temperature. Entropy of vaporization is entropy is equal to enthalpy of vaporization upon Tb, यानी कि boiling temperature. It may be mentioned here that processes like melting and evaporation involves absorption of heat, which is taken as positive by conventions of sign. Therefore, delta S for these processes is positive, that is, these processes are accompanied by increase of entropy. On the other hand, the reverse processes like freezing and condensation involves evolution of heat, which is taken as negative. Therefore, for these processes, delta S is negative, that is, these processes are accompanied by decrease of entropy. It may also be remembered, as discussed earlier, that if heat is measured in calories, the units of entropy change are calories per degree per mole. If heat is measured in calories, the units will be joules per degree per mole, or joule Kelvin per mole. Now, coming on to the last topic, that is entropy of phase change. Suppose at constant temperature N1 moles of an ideal gas 1 at the initial pressure P1 naught are mixed with N2 moles of another ideal gas 2, which had initial pressure P2 naught. Suppose after mixing their partial pressures in the mixture are P1 and P2 respectively. Now we know that at constant temperature the entropy change of an ideal gas when its pressure changes from P initial to P final is given by delta S is equal to RL and P initial upon P final mole inverse. Entropy change of the first gas when the pressure of N1 moles of gas changes from P1 naught to P1 is called delta S1 is equal to N1 RlN P1 naught by P1. Similarly, entropy change of the second gas when pressure of N2 moles of gas changes from P2 naught to P2 is N2 RlN P2 naught upon P2. Total entropy change on mixing the two gases will be N1 RlN P1 naught by P1 plus N2 RlN P2 naught upon P2. If P is the total pressure of the mixture, that is P1, P is equal to P1 plus P2, and X1 and X2 are the mole fractions of gases 1 and gases 2 in the mixture, then by Dalton's law of partial pressures, X1P and X2P, delta S mixing is equal to N1R ln P1 naught upon X1P plus N2R ln P2 naught upon X2P. Taking the simplest case in which each gas is taken at the same initial pressure and after mixing, volume of the mixture is the sum of their initial volumes, V is equal to V1 plus V2. The final pressure of the mixture will be nearly same as initial pressure of each gas, that is P1 naught is equal to P2 is equal to P. Then equation 4 is simplified to the form delta S mixing is equal to minus N1R ln x1 minus N2R ln x2. Delta S mixing is equal to minus R N1 ln x1 plus N2 ln x2. PT V1 N1 PT V2 N2 partition withdrawn, तो PT V1 plus V2 N1 plus N2 हो जाएगा. This is mixing of ideal gases. For a mixture of number of ideal gases, equation 5 can be generalized to the form delta S mixing is equal to minus R integrating Ni ln xi. To calculate the entropy change for 1 mole of the mixture, divide equation 5 by N1 plus N2, we get what we'll get? We get this equation delta S mixing is equal to minus R N1 upon N2 ln x1 plus N2 upon N1 plus N2 ln x2. Delta S mixing is equal to minus R x1 ln x1 plus x2 ln x2, which can be generalized to the form delta S mixing is equal to minus R integrating xi ln xi. From the equation, we may conclude that delta S mixing is independent of the temperature. As xi less than 1, delta S mixing will always be positive. That is, mixing of gases is accompanied by increment or increase of entropy. Now coming on to our very final topic of this chapter, that is physical significance of entropy, measurement of disorder. An examination of the various processes which are accompanied by net increase of entropy shows that they are associated with an increased randomness of distribution. For example, the melting of a solid is accompanied by net increase of entropy as already discussed, and at the same time we know that the molecules, atoms or ions in a solid have fixed positions and they become free to move about in the molten state. This is expressed by saying that there is no disorder among the molecules, atoms or ions in the solid, but the disorder sets in when the solid changes into liquid. In other words, it states that the randomness has increased. The vaporization of a liquid is accompanied by net increase of entropy as already discussed, and at the same time the disorder or the randomness also increases because the molecules of vapor are more random than the molecules in the liquid. Third is heating in a magnetized iron needle demagnetizes it because the molecules of magnetized iron needle which were oriented in a particular fashion lose the order on heating and become disordered. Fourth, all spontaneous processes like diffusion of gases, flow of heat from hot end to cold end of an iron bar are accompanied by a net increase of entropy as well as an increase of randomness or disorder. For example, in the phenomena of diffusion, the two gases which are separated initially get mixed up in a random manner. Similarly, in the flow of heat, the electrons which are separated initially, electrons present on the hot end and having higher kinetic energy rush to the cold end, thereby making the distribution more random. Hence, it may be concluded that entropy is a measure of randomness or disorder of the system. This concept may be further understood with the help of following examples. Suppose in a college, when all the classes are being held, all the students are sitting in their respective classes, rooms, and disorder is minimum. As soon as the bell rings, the students of different classes come out to go to other rooms and thus get mixed up. In other words, the disorder of the random or the randomness increases. In the game of hockey or football, second example, to start with, all the players take up some definite positions and thus are said to be in order. As soon as the game starts, the player starts running and thus they are said to have an increased randomness, which increases further as the game catches more and more momentum. So this was all about thermodynamics second. Thank you so much.